Hey there, this is Dr. Armand bringing you another exciting pre-lab lecture in General Chemistry 1 laboratories. I'm here today kicking it on the beach with my nice mask on. And so in this session here, we're going to be talking about experiment 6, the cycle of copper reactions. So we're going to start with copper. We're going to do a series of reactions. And if we do them correctly, we should end with the same amount of copper that we started with. So sit back, relax, enjoy the view, and let's get ready to roll. So in experiment 6, we're looking at the cycle of copper reactions. So in this little brief session here, we're going to talk about the different types of chemical reactions we can observe, and then the type of reactions that we're going to observe, or the actual chemical reactions we're going to observe as we do this cycle of copper reactions, and then some important experimental notes, and then we'll look through a run through of performing this experiment. So sit back and have a sheet of paper, maybe take some notes as we go through it. So we only have a few more labs left, and then we'll be finished with this lab course. So just to recap on the types of chemical reactions. So we've touched on this in earlier lab lectures or in earlier pre-lab videos, but there are two broad types of chemical reactions. We have double displacement and we have redox. And so in this lab, we'll be looking at both types of double displacement reactions. The first one is precipitation reaction. So the key thing, the key identifier for a precipitation reaction is we have at least two reactants that are solutions, so they have to be solutions. These two reactants that are aqueous, their two cations switch positions, and we form at least one precipitate, aka insoluble product. For example, we take lead nitrates, or excuse me, lead 2 nitrates, that is aqueous. We take potassium iodide, that is aqueous. So the potassium and the lead switch positions, and we get two new products, lead 2 iodide and potassium nitrate. Now, based on the solubility rules, we know that lead 2 iodide is a solid. So when you mix these two solutions together, you're going to precipitate out lead 2 iodide. And again, this insoluble solid called the precipitate, we like to describe the appearance of the precipitate. Is it flocculent? Is it gelatinous? Is it suspended? Does it settle to the bottom, etc.? So make sure you write observations when you encounter a precipitation reaction. The other type of double displacement reaction that we'll encounter, or the other type of double displacement reaction that we'll encounter, is acid-base reaction. So an acid-base reaction involves an acid and base that produces salt and water. And so for most inorganic acids, the first letter in the formula of an acid is H. And for our bases, we're talking about the soluble hydroxides, so the cation of the base and the hydrogen ion of the acid switch positions, and we get some salts and water. And water is one of the key products in an acid-base reaction. Now, we did mention early on the 6 common strong inorganic acids shown here, and as you can see, all of these have hydrogen listed first, which indicates it's an acid. So with your inorganic acids, typically the hydrogen is listed first in the formula. Now with strong bases, these are going to be your hydroxides and oxides. So an oxide, when you put it in water, converts to a hydroxide. And so that's why oxides are strong bases. And usually your group 1 and heavier group 2 hydroxides are soluble. So you will be observing both of these reactions in the cycle of copper reactions. Now, the next broad group of reactions are redox reactions. And so here in a redox reaction, we have the transfer of electrons. And the way that we know electrons are transferred is based on the changes in the charges, or sometimes referred to as oxidation numbers, of the different species on the reactant and product sides. And so you'll learn about that in the lecture, if you're taking it, how to monitor the charge or oxidation numbers between reactants and products. But the two redox reactions that we're going to encounter in this experiment is a decomposition reaction. And in a decomposition reaction, the key identifier is one reactant, and we form two or more products. Now, this reaction is sometimes redox, sometimes not. And it depends on what the compound decomposes in. So a compound decomposes into elements. For example, 2 elements. It can be more than 2, but just 2. This is redox. Or a compound could decompose into compounds. This is generally not redox. And so, excuse me. So you'd have to check the oxidation numbers, but most of the time when a compound decomposes into compounds, this is not redox. These are the two most common. And then sometimes you may have a compound decompose in a compound plus element, and this would be redox. So anytime you have an element on one side, it's in a compound on the other, redox has occurred. So in this decomposition of water, H2O is decomposed into its elements. So since it goes from a compound to elements, redox has occurred because elements in their pure state have a charge of 0. So that's one type of redox reaction we'll be encountering, and we'll let you know if this decomposition reaction that is occurring in the cycle of Copper reactions, is it redox as well. The other type of redox reaction is single replacement, and we talked about this in great depths in earlier video sessions. But here the more active element likes to replace the less active elements in a compound. So for example, we take magnesium, we put it in water. Magnesium is more active than hydrogen, so it displaces the hydrogen from the water, and we form magnesium hydroxide and hydrogen gas. Now, the way that we know that one element is more active than another element is based on the activity series. And for the lab course, as we've mentioned in previous video sessions, you have to know how to utilize the activity series, but you don't have to memorize the activity series. It'll be provided for you in questions or exams. Now, one thing to keep in mind is metals whose elements are more active, or metals which are more active than hydrogen, will react with an acid to produce a gas. And so when you take a metal that's more active than hydrogen, you produce hydrogen gas plus a salt. And it's only for those metals that are more active than hydrogen, which is found in the acid. So we'll be encountering both of these types of chemical reactions. Now, to talk about which explicit chemical reactions we're going to be observing, we'll talk about a cycle where we have different types of chemical reactions. But one thing we need to touch on as in regards to the calculations is we'll be doing solution stoichiometry. So solution stoichiometry involves molarity, and molarity is moles per volume in liters. And so in this, we'll be given some concentration, some volume, and from that, just like in this problem, we need to calculate what mass of sodium sulfate do we need and what mass of precipitate is formed. And so if we look at this, so we want to calculate the mass of solid sodium sulfate that must be added to 250 milliliters of a 0.2 molar solution of barium nitrate to precipitate out all the barium ions in the form of barium sulfate. And then calculate the mass of barium sulfate formed. And so you need a balanced chemical equation, which is what we have. And for part A, to calculate the mass of sodium sulfate, we're going to take the volume and molarity of barium nitrate, convert it to moles of barium nitrate, and then to moles of sodium sulfate, and then to mass of sodium sulfate. That's how we're going to answer part A. Part A. In part B, similar to this, we're going to take the volume and molarity of barium nitrate, convert it to moles of barium nitrate, convert it to moles of barium sulfate, and then to mass of barium sulfate. So again, when we have volume and molarity, molarity is moles per liter. Volume needs to be in liters. So here if we start with volume is 0.250 liters. Well, then remember molarity is moles. So we can rewrite 0.200 molar as 0.200 moles equals 1 liter. So since we're starting with liters here, we can put 1 liter on the bottom and 0.2 moles on top of barium nitrate. That's step 1. The next step is now we have moles of barium nitrate. We want to convert it to moles of sodium sulfate. So what do we know? We know that 1 mole of sodium sulfate needs 1 mole of barium nitrate from the coefficients in the balanced chemical equation. So we know that 1 mole of barium nitrate needs 1 mole of sodium sulfate. So now we have the moles of sodium sulfate, then we need the mass of sodium sulfate. And so we need the molar mass of sodium sulfate. It's 142 grams. So 142 grams of sodium sulfate equals 1 mole of sodium sulfate. Since we're starting with moles on the top left, the mole goes on the bottom. And the mass goes on top. Everything on top you multiply, everything on the bottom you divide by. And we get 7.10 grams of sodium sulfate. Now moving on to B, we're going to set up B the same way. We're starting with volume. We want to convert that to moles of barium nitrate. So we know that 1 liter, 0.200 moles of barium nitrate. Now that we have moles of barium nitrate, we're going to convert it to moles of barium sulfate. Again, if we look at the balanced chemical equation, 1 mole of barium nitrate gives us 1 mole of barium sulfate. Next, we need to convert this to mass. So we need to know the molar mass of barium sulfate. So we know that 233.3 grams of barium sulfate is equal to 1 mole of barium sulfate. Now, since we're starting with moles of barium sulfate on top, it's going to go on the bottom in our next train track. So we get 11.7 grams of barium sulfate. And this would be called the theoretical yield. So again, with solution stoichiometry, either at the beginning or at the end, you're going to be using the molarity equation. So now, what actual reactions are we going to be doing in this cycle of copper reactions? So pay attention here. This is important. So let's say we start with 1 gram of copper. When we do the cycle of copper reactions, we should end up, if we did everything perfectly, we should end up with, that's right, 1 gram of copper. So in the first step, you're going to weigh out your mass of copper. You're going to react it with concentrated nitric acid plus the oxygen in the atmosphere. And what's going to happen is you're going to convert this copper metal into copper 2+ ions. So remember that nitric acid is a colorless solution, and copper 2+ is a blue solution. So you're going to see the solution go from colorless to a creepy green color to a blue color. And the blue signifies the presence of copper 2+ in water. So that's step 1. So step 1 is a redox reaction. So this is a redox reaction. The way I know it's redox is because we have elements and they become ions. Step 1. In step 2, as we move through our cycle, you're going to take that solution of copper 2+ and you're going to react it with a solution of sodium hydroxide. And what's going to happen is the hydroxide will react with the copper 2+ and will precipitate out copper 2 hydroxide. And this is a solid, it's like a gel-like blue solid. So again, we're going from a blue solution to a blue solid. And this is a precipitation reaction. So step 2 is a precipitation reaction. We're going from a blue solution to a blue solid when we add sodium hydroxide to copper 2 plus ions. And that's because, again, copper 2 hydroxide is insoluble. Go to the next step. So then we're going to take this copper 2 hydroxide. We're going to heat it to form copper oxide. So this third step is a decomposition reaction, but it's not redox. So we decompose the copper 2 hydroxide, which is a blue solid, to a copper 2 oxide, which is a grayish black solid. And the other product that we produce, because remember we have to have 2 or more products, is water vapor. And so in step 3, we decompose copper 2 hydroxide into copper 2 oxide. So we go from a blue solid to a dark gray black solid. So that's step 3. In step 4, we're going to take our copper 2 oxide, it's an oxide, and we're going to react it with sulfuric acid. Now remember I said earlier that oxides can behave as bases as well. So we're going to react this copper 2 oxide with sulfuric acid. This is our acid-base reaction. So step 4 is the acid-base reaction. And so we go from a black solid to copper 2 plus ions in solution. So this is going to be a blue solution. So we go from a black solid to a blue solution again. And now the last step is to reclaim our copper. So we're going to, in the 5th step, we're going to add zinc to the copper 2 plus solution. So the zinc is more active than copper. So it's going to react to form zinc ions. And you're going to get copper metal. And remember, copper is a orange solid. Now, what also you'll notice is that the solution will be colorless because zinc 2 plus solution is colorless. So this is a single replacement reaction. So I've written here the types of reactions in each step, what you should be observing. So these are things you should write in your lab notebook as you're doing these different steps. Now, if you start with 1 gram of copper, if you do all the steps correctly, in theory, you should end with 1 gram of copper. And just a few things in this experiment, we will be using concentrated acids and bases. So please make sure that you're very diligent in handling these types of acids and bases. Like 16 molar HNO3 is very, very strong acid. 6 molar H2SO4. These are very hazardous reactants. So if you do spill these on your hands, immediately wash off with copious amounts of water. Also, it's highly recommended that you wear gloves as well. So down here is an example of a severe acid burn. And in one of the last steps, when you're drying or you're washing your copper, you may be using liquids such as methanol or acetone to help wash your copper product. So make sure you heat it on a hot plate or in the oven. Do not use a Bunsen burner because these are flammable liquids. And lastly, the first step when we add copper wire to nitric acid, the concentrated nitric acid, it produces nitrogen dioxide, which is a toxic brown gas. So make sure you do this in the hood. So this is the first step when you add your copper to your nitric acid or your nitric acid to your copper. Make sure you do this in the hood. It takes, quite a while because you have to kind of wait for the copper to react completely. So make sure you do that part in the hood. Now, besides the 16 molar nitric acid, the 6 molar H2SO4, 6 molar HCl, 3 molar NaOH, we will also be using zinc, metal, sodium hydroxide, a solution. We'll be using such solvents as methanol and acetone to wash the copper. We'll be dealing with copper 2 hydroxide and nitrogen dioxide gas. So we'll be handling a variety of different types of chemicals in this experiment. So now we're going to show you kind of a practice run of completing this lab. So the first thing we want to do in this experiment is to weigh out our copper. So again, in the lab, it'll tell you how much copper metal to weigh out. So that's what we're doing here. Make sure your balance is tiered, 0 out. So now we're going to weigh out the copper. So we're going to remove the mass of the weigh boat. And make sure, if you can, try to cut the copper into small pieces. It works better. So in this example, I'm going to weigh out about 0.6 grams of copper. So you can use wire cutters to cut the copper into small pieces. The smaller the pieces, the easier it is in reacting with the nitric acid. It kind of works a little bit better when you have smaller pieces. And then we're going to add the copper to the beaker and then go to the hood and add the 16 molar concentrated acid. So we're here in the hood. There's our 16 molar concentrated acid. We need to measure, I think it's 5 milliliters of the concentrated nitric acid. And as you can see, we're already seeing the reaction occur. The solution is turning a creepy green color. We have nitrogen dioxide being released from the reaction. And over time, you see the reaction goes to a blue solution, indicating the presence of copper 2 ions. So you need to keep reacting the copper until all of it is reacted and it looks like a nice aqua blue solution. So that brown gas is the nitrogen dioxide. So now that all the copper has reacted, we're going to add some DI water to the beaker to give it a little bit more volume. And it looks something like this. So again, once all of it, the copper has reacted, you get this blue color solution. Then we add DI water to the beaker. And in the second step, remember, that's when we add the aqueous sodium hydroxide shown here, and we get this blue precipitate. So this is step 2. Let me go back a little bit so you can see that again. So be watching here. We're going to add the aqueous sodium hydroxide, and you're going to see a dark blue precipitate form. So this is the precipitation reaction between sodium hydroxide and copper ions. So we'll leave this for a few minutes to react, and then the next step would be to heat it so that we can do the third step. So again, see the blue precipitate in the beaker. So that dark blue precipitate is copper 2 hydroxide. You may want to stir it a little to make sure the reaction goes to completion. So next we want to place it on the hot plate, and I've kind of time-lapsed this, so it takes a little while. You want to see the blue solution, or excuse me, the blue precipitate turn to a black precipitate. So once all the blue precipitate has turned to black precipitate, this is step 3, the decomposition reaction. So we're taking copper 2 hydroxide, we're heating it. It gets converted into copper 2 hydroxide, which is a black precipitate. So you want to make sure all of it has been decomposed into copper 2 oxide before you move on to the next step. And so over time, it turns to a black precipitate. So after 10, 15, 20 minutes, we get this black precipitate, which is the copper 2 oxide. So now we've done the decomposition reaction. You can see behind it in another beaker, that's the initial color, the blue color, and then, or the blue precipitates. As you heat it, it turns to a black precipitate. You want to let it settle to the bottom, because now we're going to have to remove that top layer of liquid or solution from the beaker. So this is the product of the decomposition reaction. So here you can kind of see the before and the after. So this is the before, and this is the after. So this is when you stop, you're going to let it settle to the bottom, and you're going to use a dropper and kind of remove or decant the solution from the product. So next you want to decant off as much of the solution as you can into a waste beaker. And once you get near the precipitate, you want to use a dropper and kind of remove as much of the solution as you can without picking up any of the product. So here this TA is using a dropper to get as close to the product, or to remove as much of the solution as they can without extracting any of the precipitate from the solution. It's a very tedious process, but diligence is needed here so you don't pick up any of the precipitate. So he's adding the hot water to the solution, to the precipitate, to wash it, to get out any residual of the solution that's left. And so again, you let it settle and you go through the same setup as before. Once it settles, you try to discard or decant as much of the solution as you can while leaving the precipitate in the beaker. So he added some hot water to the beaker there, and now it's going, once it settles, is going to decant the solution. So after several minutes, it's settled. So you see there's a big gap between the top of the solution and the precipitate. So here you can pour out, decant some of it before using the dropper if you like. Or you can just get a dropper and start with the dropper at this point. But the student here decided to decant. So we're going to watch the student decant some of the solution from the beaker. You got to be careful here not to lose any of your precipitate from it. So once it gets close to the level of the precipitate, we're going to use a dropper to get out the remaining solution. So try to be very careful here. We don't want to extract or to pick up any of the precipitate while we're doing this stage. It's very important that we be very careful here. So I kind of fast forward, it was, several minutes. It's a very long process to carefully remove as much solution as you can. But here we're near the final, the end of this process of removing the solution. And now we're going to add the sulfuric acid. And here the sulfuric acid mixed with the copper 2 oxide is going to be our acid base reaction. So we should see the black precipitate react, and you're going to form a blue solution. Remember, this is 6 molar H2SO4, and it takes a little bit of stirring the precipitate with the sulfuric acid. But you see we go from a black precipitate to a blue solution, indicating the presence of copper 2 ions in solution. So this is the 4th step, or acid base reaction. A nice here color change from a black precipitate to a blue solution. Next, we're going to add the zinc metal into the solution so that we can do a single replacement reaction and exchange the copper ions for zinc ions, and the copper will precipitate out of solution. And the reason that copper will be exchanged by zinc or replaced by zinc is because zinc is more active than copper. So zinc will replace copper in solution. And what you should see is over time, the solution should go from a blue color to a colorless color, or to a colorless solution. So it does take some time for the zinc to completely react. And in the process, you're going to be forming a red-orange precipitate, which is copper. So we're extracting back out the copper from the solution. And as you can kind of see, the blue color is slowly losing intensity as the reaction is progressing. And so this is the single replacement component of this lab. So a lot of students like this lab because we see a lot of different color changes, precipitates forming. while this lab is being conducted. So it's a very exciting lab. Uses a lot of different lab techniques as well. So this process does take a few minutes to complete. So after several minutes, you start seeing you notice that the blue color is mostly gone from the solution, and we have our reddish brown precipitate, which is copper metal. So don't be surprised that some of these steps take a long time. You kind of seen a time lapse of this experiment. So now we want to pre-weigh the weigh boat. Or the evaporating dish. So let me record that mass for the evaporating dish. We're going to need it at the end to calculate the mass of product produced. So the mass of the evaporating dish. So make sure you do take the mass of the evaporating dish. And so we're going to have to wash the copper now and place it into the evaporating dish. So now we need to wash the copper and we need to transfer it from the beaker to the evaporating dish. So you can see the copper in the beaker. So we're very carefully going to put it into the evaporating dish. Kind of swirl the beaker, get the copper moving from the bottom of the beaker. So now we're going to remove the water out of the evaporating dish using a dropper. Be careful not to pick up any of the copper in the evaporating dish. This is very tedious, but it's very important that you do this carefully as to not lose product while you're removing the solution. And we'll get the rest of the copper out of the beaker in just a moment. So now we're adding some of the methanol or acetone we're using to wash the copper. We're going to swirl it around and then pour it into the evaporating dish to get the rest of the copper out. That's a good way when you're washing, just add the solvent that you're using for washing into the beaker, swirl it around, and then pour it into the evaporating dish so that it washes the copper as well. Very important that you wash your product because we don't want dirty product. So now all of the copper has been transferred to the evaporating dish. So again, we're going to have to remove the solution that's still in the evaporating dish with a dropper and then place the copper in the oven to dry it. So that the person does one more washing of the beaker. You're using like 5 milliliter portions of methanol or acetone, whichever one's available, to wash the copper. Washing is extremely important. Notice we have a waste beaker that all our waste, aqueous waste or solution waste goes in. So again, this process does take several minutes. I kind of time lapse through it. But again, you have to use the dropper very carefully, remove all the solution, because the more you remove, the better the drying will occur in the oven. So it is a very tedious process that you have to take your time and patience with. See how diligently this TA is at getting all the solution out of the evaporating dish. Once all the solution is out, then we're going to place it in the oven to dry. So here, as much of the solution has been removed as is possible. So the next step is to place this in the oven and dry the copper. Again, we're doing one more washing and extracting out the solvent. So in this washing, unlike the previous ones where we were using water, that was my mistake. So in the previous one, we were using water. Here we're using the methanol / acetone because it's in its own beaker. So organic solvents have their own waste container separate from the other waste containers. So again, before this step, we were washing with water, not the methanol or acetone, because the methanol and acetone, they go in a separate waste container because they're organic solvents. So you do a few washings with the acetone or methanol. So after drying it in the oven, you let the evaporating dish cool down to room temperature, and then you take the mass of the evaporating dish and the precipitate, copper. So here it's 40.83. So again, we put it in the oven, we dried the copper. We got a mass of 40.83 grams. Again, make sure the evaporating dish is to room temperature before you place it on the balance or mass of recovered copper. It's just a difference between the two. .34 grams of copper was recovered. Remember, we initially started with 0.61 grams of copper. So our percent recovery is our mass recovered divided by what we started with times 100. and it's about 55.7%. So obviously we lost half of our product somewhere in the steps. So if you don't get near 100% recovery, you need to think about where you may have made mistakes in the experiment. Was it the washing? Was it the extracting of the solution, etc.? One last thing is the way you know that your copper is dry is that when you take the evaporating dish and kind of move it with your hand, the copper moves freely in the dish. It's not clumpy. So that's a good indication to know when your copper is fully dry. And as far as the waste, please make sure to put the copper in the solid waste, not in the glass bottles. There will be a white container that'll say copper waste, copper solid waste. Make sure you put the copper solid waste into the solid waste container, which is usually a white plastic container or a beaker. The solutions that you extracted at all the different points in the lab should go in the aqueous waste, usually a glass bottle. And the organic solvents that you use for washing usually will have their own separate container as well. So make sure when you're getting rid of your waste that it goes in the correct waste containers. So for the solid, it has its own solid waste container for the copper. For the organic solvents such as methanol and acetone, they have usually their own separate waste container. So make sure you read the label. It'll tell you what goes in each waste container, because if you mix waste, it becomes more expensive for us to have it removed. And so this is pretty much all the calculations you're going to be doing in this lab. So that's all for lab 6. I hope this session was informative. You're able to learn some of the background to the lab, some of the experimental steps in the procedure, and that you feel that you're a little bit prepared to perform this lab in the coming week. So on that note, that's all I have for this session. This is Dr. Armand signing off until next time.